Hey guys, welcome back to General Chemistry. Today we're going to talk about one of the more difficult topics in Chapter 6, and that has to do with titrations. So, titration falls under what we call a quantitative chemical analysis. So, quantitative chemical analysis is determine the amount or concentration of a substance in a sample. So, essentially, we have an unknown. We want to know something about it. Upper level chemistry really is just piecing different pieces of a puzzle together. So if we can determine the concentration or the amount of the substance that was present, that might be one of the pieces of the puzzle that we need. There's two common quantitative analysis. Titration is going to be the one that we focus on. There's a gravimetric analysis, but we don't talk about that in this class. So today we're going to introduce that titration. So a titration is defined as such. A substance of a known concentration is reacted with a substance of an unknown concentration. So we're trying to determine how much of something we have, and we're going to use something that we know to get us that information. So known to find unknown. There are different types of titrations that we can do, so a multitude of different chemical reactions that we can create to do this known and unknown balance. The most common type of titration, though, is an acid-base titration. So using an acid to determine a base or using a base to determine an acid concentration. So let's consider the following chemical reaction. I'm going to give you guys just a second to write down this chemical reaction because it's the one we're going to use as our example. So in this example, we've got hydrochloric acid, that's our HCl, reacts with sodium hydroxide, that's our NaOH, and we produce water and sodium chloride. So hydrochloric acid, sodium hydroxide. So here's what a titration is going to look like. Practically, how are we going to perform a titration? For these problems, my biggest recommendation is to draw a picture. So what I want to do now for you is kind of set up that picture in your head. So in a titration, we're going to have what's called a burette. So this thing right here is called a burette. We're going to have some sort of flask at the bottom. And we are going to drip, drip, drip whatever is in the burette into our flask. And at some point, the color is going to change. So that's kind of the general outline of a titration. In the burette, so in this device right here, we're going to have what's known as the titrant. So that's the solution that we know. So in the burette is going to be whatever it is that we know. The burette has one job, and that's to measure how much liquid we're putting into a solution. So as I open it up and it drip, drip, drips in, we can monitor exactly how much of this solution goes in. And then at the end, when we start mathing with it, that's going to be an important number. How much of our known did we actually use? Down here in our flask is where our unknown will go. We may not know the concentration of that unknown, but we will know exactly how much we're starting with. So when I have that flask down there, I might say, okay, I'm going to put 20 mils of hydrochloric acid in there. Or I'm going to put 10 mils of hydrochloric acid in there. So we'll know how much of our unknown is in here. We just don't know its concentration. Okay. So we drip, 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 drip. And there's got to be some point where we're like, okay, boom, that's the end of the experiment. That's where it stops. And that point is going to be called the equivalence point. In this case, the equivalence point is denoted with a color change. It could be monitored in some other fashion, but typically when these are first introduced, that color change is how we determine, boom, stop the reaction. Once we reach that equivalence point, that's going to be a very important place for us to understand. So in the equivalence point, the number of moles of our known is stoichiometrically equal to our unknown, or what is being analyzed. So what that's doing is that's just a fancy way of saying, at this moment, boom, stop the reaction. I can set up a ratio between my known and my unknown based on stoichiometry, based on balanced chemical equation. So this equivalence point is going to allow us to do the following. So remember that map that we looked at last chapter that was like grams to moles to moles to grams? What this equivalence point is going to allow us to do is just this step right here, okay? So the equivalence point tells us that the number of moles of our known is in ratio with the number of moles of our unknown. So we can set up that mole to mole ratio to get from units of known to units of unknown. That's a very important piece there. Okay. All right, so I think the best way to do titration problems really is just to dive in, to jump into an example. There's going to be a mantra that we use for these titration problems. So what you'll see is there's a lot of steps, a lot of things to keep track of. The math is not terribly difficult. It's really straightforward algebra. But what's hard is keeping track of all the different moving parts. So I've created a mantra to help us with that. It's a 3-step mantra, which you'll see to the side as we start to work through this problem. So here's our problem. Suppose 22.4 milliliters of 0.1 molar sodium hydroxide is needed to reach the equivalent point or endpoint in 100 mils of our unknown hydrochloric acid. What is the concentration of hydrochloric acid? Our mantra out to the side you'll see is molarity, moles, molarity. So we're going to solve these problems in 3 steps. But before I start to solve the problem, I want to get a picture onto the board. I want to start to get a clear look at what we're solving for, what we know. Okay. So let me set up my titration over here. So I've got my burette. I've got my flask. Okay. And in my burette, remember, is going to be our known substance. And in the flask is going to be unknown. Now we look back at the problem and decide what's known and what's unknown. So our known, the concentration will always be given. So this 1.1 molar sodium hydroxide, that identifies that as our known. So I'm going to put that in my burette. So 0.1 molar sodium hydroxide. Okay. The last piece of information that I also know about that particular substance is I know exactly how much I put in, right? Open it up, drop, drop, close it. Open it up, drop, drop, close it. And eventually that ended with 22.40 milliliters. Okay. Now we're going to come down here and fill in our unknown. I'm just going to change the color so it matches. Okay, so in this case, our unknown. So we use sodium hydroxide, needed to reach the endpoint. We've got 100 mils of unknown hydrochloric acid. So I'm going to put that down here. I know that it's hydrochloric acid. I don't know what the concentration is, but I know that that's the substance. And I also know how much I started with. I know that I started with 100 milliliters of it. Okay, and that's all I know about that so far. All right, good. Now we have our picture. Now we can go over to our mantra. So our mantra is molarity, moles, molarity. First molarity tells us two things. One, we're going to use the molarity equation, right? So that's going to help us with that. We also need to know, okay, are we going to start our calculations? Do you think we're going to start them with the substance that we don't know anything about? Or are we going to start with a substance that we know some things about? Yeah, probably one we know some things about. So we're going to start with the molarity equation, and we're going to start with the numbers that we know. Okay. This moles, so molarity, moles, molarity. In this step, we're doing that mole to mole ratio. And here's where we're changing from our units of known to unknown. So that's how we get from the substance that we know a little something about to the substance that we don't know anything about. And then in the last step, molarity. So that word tells us that we're using this equation again. And now for molarity, we're going to be inputting the information of our unknown substance. So we'll know just enough to be able to use that equation and solve for the piece that we need to know. So that's the conceptual path through this problem. Let's go ahead and start chugging our way through it. Step 1, molarity. I'm using this formula. I'm going to be inputting information about my known, so let me take inventory of what I know. All right, so my known is over here in my burette. This is the information I know. So do I know the molarity? I do. I know the concentration, and my problem told me it's 0.1 molar. Is there any mention of number of moles here? No, there's not. Is there any mention of grams that would get us to moles? No, there's not. I wonder if that's what we're solving for. And then the last variable here is volume. So do I know how much of the known that I put in? Yeah, absolutely. That's the whole purpose of the burette. But be careful. Molarity equation. What is the unit that we're dealing with? Yeah, we got to transition that into liters, right? So you can divide by 1,000. You can move the decimal place over 3 places. Whatever trick that you have, make sure you get used to it because you're going to be doing this a lot in this chapter. All right, so we're putting 22.4 milliliters. We used that. So transition that to liters, and it's 0.0224 liters. Okay. So looking at this information, it must be that I am solving for number of moles, and that's exactly what we're solving for. So let me plug this into the equation here. I'm going to clean it up. All right, so we've got 0.1 molar. We've got N on the top, and we have 0.0224 liters on the bottom. So algebraic rearrangement, I'm going to multiply by 0.0224 to get that out of my fraction. Whatever I do to the right side, I also have to do to the left side. So we're going to multiply 0.0224. So then we're going to get that the number of moles equals 0.1 times 0.0224. And we get 0.00224 moles, and then we can put of what? Of Na Okay, that's step 1. Done. All right, step 2. Step 2 is where we are going to go from our moles of known to our moles of unknown. And to do this, we're going to set up a train track. Okay, so I'm going to start with the information from step 1. So I have 0.00224 moles of NaOH. I'm doing that mole to mole ratio, so I'm going to do my train tracks here. Little to no thought, moles of NaOH go on the bottom. Okay. Now I just need to go back. I'm going from moles of my known to moles of my unknown. So looking at my picture here, we're going from sodium hydroxide to hydrochloric acid. Okay? So we need to use this balanced chemical equation and look at this ratio between these two. Okay? So let me get my destination onto the top. This is going to be moles of HCl. Okay? When we do this mole to mole step, what numbers did we put in there? Where did we go to find those numbers? We go to the coefficients from the balanced chemical equation. So this one, and it's not always going to be the case, this one happens to be a 1-to-1 ratio. So the coefficient for both of these is 1. So we have 1 mole of hydrochloric acid, 1 mole of our sodium hydroxide. So we multiply across the top, divide by the bottom, and the answer to this one is 0.00224 moles of now HCl, are unknown. Okay. All right, so we're going into our last step. So our last step is we're using the molarity equation, and we're inputting what we know about our unknown. So I'm actually going to do it right here in the middle again, just so we have our picture close. So from step, actually let's get the molarity equation on the board. So we have molarity equals N over V. Okay. I'm going to take inventory of what I know, try to decide what it is that we're solving for. Is there any mention about the molarity of our unknown solution? No. That's literally what we're solving for, right? It's saying, what is the concentration? So that is the whole purpose of this exercise, is to solve for the molarity. So we must have the other two pieces. Number of moles. Well, number of moles is not mentioned in the problem, but if we look at step 2, what did we solve for? Yeah, we solved for number of moles. So the answer from step 2 is 0.00224 moles of the unknown. Okay, so that's the purpose of step 2. And then lastly, do we know the volume? Well, of course, we know exactly how much of that substance we started with. But again, be careful. We're not using milliliters. We want to make sure that we're using liters. So we started with 100 milliliters of hydrochloric acid. So putting that into liters, it's 0.1 liters. Okay. Now we have the variables. We just need to plug it into the equation and chug our way through it. So molarity equals our number of moles on top, 0.00224 moles. Liters on the bottom, so 0.1 liters. So the molarity of our unknown substance, 0.00224 divided by 0.1, and we get the molarity is 0.0224 molar. That is our answer. So again, the algebra at each step is not terribly difficult. The hard part is juggling all the variables and then finding a logistical path through this. Hopefully you guys write down this mantra: molarity, moles, molarity, and that'll help guide you through the problem. I hope you guys found this helpful.